Thank you, Erica, for the kind introduction and also hosting us in Seoul. We have two team members actually who are from South Korea, and they're totally amazing engineers, and I'm really happy to be here for the first time, so thank you for having me. Today I'm going to be talking about what is zk, what are zkVMs and zk rollups, and then also zk and the broader Ethereum roadmap. And that's obviously what we're all building at Succinct. So maybe just start off with a brief overview of zk, because I think for some audience members, maybe you've heard the term, but you don't know exactly what it is. zk is actually a pretty simple concept to understand. At its core, it's a cryptographic primitive that lets one party approver prove to another that a statement is true without revealing any additional information. And in particular, it has two properties: the succinctness property, which is what our company is named after, where the verifier can verify the proof of a statement in much less time than it needs to redo the computation. And then there's also the zero knowledge property, where the prover can hide inputs to the computation to preserve privacy, so the verifier never knows the values. And so those two properties, succinctness and zero knowledge, make zk very useful for scaling blockchains and also for preserving privacy on blockchains, which generally, by default, operate as fully public, transparent ledgers. Okay, and then zk has been kind of universally acknowledged to be useful to blockchain scalability and privacy, but historically, it's been really, really difficult to use. So on the left-hand side, there's kind of like the old way of doing zk, where you have to write these things called circuits. It's very complicated, it looks very arcane, it's not normal programming language. And then with what we built at Succinct, it's called a zero-knowledge virtual machine, or zkVM for short. You can use zk by just writing normal code. So on the right-hand side, using SP1, you can just write normal Rust, and you can write your program or statement you want to generate a proof of in normal code, normal programming language, and then get a proof, putting it through our zkVM called SP1. And that's really awesome because it makes zk accessible from something that used to be only hundreds of developers in the world can do. It took a very long time. It required a cryptography PhD, to something that an average developer, millions of Rust developers, can now all use zk and prove whatever computations they want. And SP1 is really special because not only does it make zk super easy, it also makes zk very fast and very cheap. So it has great performance. So this is kind of a diagram showing SP1's performance since we released it around a year ago to now. And since then, by metrics, we've improved SP1 between 20 to 50x depending on how you're counting it, and there's no sign of that slowing down anytime soon. And that's really awesome because zk needs to be cheap and fast for it to be actually scalable and useful for all the things we want to use it for, like rollups or scaling Ethereum. And then final piece of the puzzle is the Succinct network, which is the protocol we're building to make using SP1 very easy. So when you generate a zk proof, you can't really generate it on your laptop for the most part when you use a zkVM. You have to use a GPU or other hardware to generate it efficiently. And that's not something most people have readily accessible like in their homes or in their offices. And so the Succinct network is incentivizing this global distributed hardware build-out where we have a bunch of provers all across the world running on data centers, running GPUs, maybe in the future running FPGAs and ASICs, similar to kind of the Bitcoin mining build-out, to generate zk proofs and provide them to users of zk like rollups and other blockchain systems. And on one end, you have the applications that use zk, so bridges, L2s, oracles, and then even other use cases outside of crypto or in blockchains. They use SP1, and then they send proof requests to the network, and you have proving pools and other data center providers all across the world who are generating these proofs and providing them back to the users. And the network coordinates all this activity and facilitates payments between the parties and settlement and price discovery and things like that. So I like to say that with what we're building at Succinct, our zkVM and our prover network, it kind of lets zk become ready for mainstream adoption. Finally, you have that zk is actually easy because you can write normal code and get a zk proof. It's cheap, it's fast, and it's one click. You can just send a request to the network and get it back. You don't have to set up your own infrastructure. And zk's been around for a long time, so I like this diagram to show the difference between how zk used to be, zk 1.0, and with our zkVM and the network, what zk is now, which I like to call zk 2.0. So in zk 1.0, which is kind of the existing paradigm of zk rollups, things like Starkware or zkSync or Polygon, you have these whole companies who made their own zk proof system, who deployed their own prover service, and who had to build everything themselves to make a full zk rollup. Now with zk 2.0, with zkVMs and our prover network, zk becomes much more simple. If you're an application team that wants to build a rollup or some sort of other zk application, like a verifiable exchange, for example, or verifiable perp dex, you can just write your application logic in normal code, you can plug it into our zkVM, send requests to our prover network. You don't have to set up any of your own infrastructure. You don't have to hire a team of cryptographers. You can just write your application and go. So in zk 2.0, zk's general purpose, it's fast, and it's really easy, and I think that's the reason we're going to see this turning point in zk adoption over the upcoming year. So with zk 2.0, this talks at ETH Seoul, so I wanted to talk about its impact on the Ethereum roadmap. And obviously a very popular topic in the Ethereum roadmap these days is zk rollups. So now I'm going to talk about why kind of this new paradigm of zk lets every rollup be a zk rollup. So first, I think it's important to acknowledge that most of the rollups on Ethereum today that are very popular, for example, Arbitrum, Optimism, Base, are all optimistic rollups. They're not zk rollups. And a big question to ask is kind of, why is that the case? So back when the rollup-centric roadmap was really in full steam a few years ago, zk was very difficult. It didn't have the properties that zk has today with zkVMs. It was very hard to deploy. You needed that big team of cryptographers. And so in some ways, when those rollup teams wanted to go to market quickly, they had to choose this other technology, optimistic rollups, for their security properties, and that kind of led to some bad trade-offs. So they were able to go to market faster and accumulate TVL, and that's why those rollups are some of the most commonly used rollups today. But the cons of the optimistic fraud-proof system are that you have a very long finality time for bridging assets to and from the L1. So in particular, you have this 7-day withdrawal window where if you're a user, you deposit funds into the rollup. To get it out from the rollups bridge, you need to wait 7 days for the optimistic challenge game to play out. And that's really bad because it locks up capital, it degrades user experience, and it also makes interoperability between Ethereum rollups really hard. And I think a lot of the problems and discourse around Ethereum interop and fragmentation are due to this fundamental shortcoming of the optimistic rollup systems. Additionally, the optimistic systems are actually pretty complicated to implement and build. They involve this thing called fault-proof VMs, and they're very complicated, lots of code. And they're actually really complicated to reason about as well, because it's kind of this niche area that's only useful for blockchain bridging, whereas zk, for example, is a very well-studied academic field with a lot of people, even outside of crypto, kind of interested in it. So as I was mentioning, the optimistic rollups are very popular today for kind of the path dependency reasons that I mentioned, where it was fast go-to-market, but a bunch of other technical trade-offs. And with zk 2.0, we've kind of removed all the old trade-offs with zk. So it used to be that you needed a whole team with cryptography PhDs to implement the zk circuits to implement your rollup state transition function. But with SP1, you can just write normal Rust code and implement it, your rollup state transition function, and get a zero-knowledge proof that you can use for your rollups bridging. Then you'd have to set up your old proving system in the old way of doing zk, and you'd have to deploy it yourself, set up your own GPUs, and go through a lot of effort. But with the Succinct network, you can just take your program, deploy it to the network, and get proofs for it basically instantly, which is really awesome. And finally, the last problem with upgrading all the existing optimistic rollups to zk is once you have a rollup live, there's a bunch of TVL in the bridge, it's really hard to actually transition those systems to new systems. And so a lot of optimistic rollup teams have kind of had to stay with the old technology. But with SP1 and our zkVM, you can just take your existing stack and upgrade it to zk with something called OP Succinct that I'll talk about in the next slide that makes the transition actually very seamless and smooth. So OP Succinct is kind of our first step to integrating this zk 2.0 vision into all of rollups. And in particular, what it does is it takes an existing, very battle-tested rollup stack, the OP stack, that's used by Optimism and Base and Unichain and a bunch of other rollups. And it basically takes the code for OP stack that's written in Rust, sticks in SP1, uses the network to generate proofs. And in all, if you're a developer that's using an OP stack chain, you can get a simple one-click upgrade to zk. and you reduce your finality from 7 days to just as fast as 1 hour, and maybe in the future as fast as 10 minutes, and better security. So it's really simple. You just combine this existing rollup stack that's really battle tested. You upgrade one smart contract that changes where your bridge points to a bridge version that verifies the zk proof, and you get all these benefits. And I think overall, OP Succinct shows that every rollup can be a zk rollup because you can upgrade existing technology to use zk very easily. And moreover, because we can take all this existing infrastructure and upgrade it seamlessly, it gives a much easier path for teams to actually adopt zk this time around. They don't have to do complicated, long changes. They can just do this seamless one-click upgrade. And OP Succinct adoption we have a bunch of teams who are using it. So we have a mainnet for this chain called Fala that's building TE-powered infrastructure on their rollup. And they've had an OP Succinct mainnet smoothly working since January. And Mantle recently announced that they're going to use OP Succinct, and they actually have it live on their testnet. And they're one of the biggest L2s on Ethereum with over $2 billion in TVL. And we have a bunch of infrastructure partners who are using OP Succinct as well and support it, which is really awesome. And this kind of shows that a broader trend of OP Succinct being the first step in converting all Ethereum rollups to zk. So now hopefully I've convinced you that zk 2.0 is just going to make every rollup a zk rollup, solve a lot of Ethereum's fragmentation problems, upgrade all existing optimistic rollups to this endgame infrastructure. But now I'm also going to talk about zk in Ethereum's broader roadmap beyond just zk rollups. So one very key property that Ethereum has is it really prioritizes verifiability. And this is actually something that's fairly unique to Ethereum, where the vision of Ethereum is in the future, you can have everyone running an Ethereum light node on their phone, where they basically download block data and download a bunch of snark proofs and verify them, and then they're verifying the chain themselves. And so in Vitalik's very large Ethereum roadmap diagram, one of the biggest squares is the verge, and it's focused a lot on verifiability, and you can see the pink highlighted parts are all the relevant parts where zk helps Ethereum be more verifiable. So the goal is verifying blocks should be super easy. You download a few bytes of data, you verify snarks, and then you know that what the tip of the Ethereum chain is and what the canonical state root is. And you can see a lot of the things to get there include snarking the execution layer, snarking the consensus layer, and having a fully snarked Ethereum, which I think with SP1 and zkVMs broadly today is actually pretty easy because you take Rust implementations of the execution and consensus layer, stick them in a zkVM, and generate proofs. So we're well on this roadmap to actually execute on it with zkVMs. The other exciting thing that's been talked a lot about recently in Ethereum's roadmap is real-time proving and native rollups. So I'm going to also dive into that a bit. So first, let's talk about what is real-time proving. So real-time proving is the idea that we want to generate a zk proof of Ethereum block execution in under 12 seconds, which is the Ethereum block time. And how it's implemented is we take a Rust Ethereum client called Reth. So it's the Rust implementation of the Ethereum block execution. You stick it in SP1, and you generate proofs of execution. And I'll talk a little bit about why we want to do this later and how it relates to native rollups. But first, let's just talk about how we actually implement this. So basically, you take an Ethereum block that's part of the chain. You get a bunch of Merkle proofs, which are useful for getting all the state proofs that you need to prove relevant state against the old block header, and you run the execution natively. Then you take all of those inputs and you stick it in an SP1 program that uses Reth to actually generate a proof of execution. So it'll take in all the Merkle proofs, it'll verify the state it's accessing during that block execution. It'll actually run an EVM interpreter written in Rust. It'll fetch the relevant bytecode and execute all the smart contracts. And then at the end, it will compute the new state root, a new block header of the world. And it'll all be run on a bunch of GPUs that are doing SP1 proving. And the goal for real-time proving is to have that step after you fetch the inputs and you actually generate a proof to take less than 12 seconds. And we're actually pretty close to being able to achieve this today. So if you look at Ethereum blocks, these are sample Ethereum blocks. One is 15 million gas, which is kind of the average block gas of an Ethereum block. One is 30 million gas, which is kind of the max gas limit today. You can see that on the latest version of SP1, we're pretty close to 12 seconds. So for the 15 million gas block, it's 23 seconds. For the 30 million gas block, it's around 30 seconds. And we think that we can hit real-time proving over the next few months with further performance optimizations. So we're getting pretty close to this goal of achieving real-time proving, of generating these proofs of Ethereum blocks, any Ethereum block, in less than 12 seconds. Now, why is real-time proving interesting? So the reason a lot of people in Ethereum are excited about real-time proving is to implement this concept known as native rollups. So native rollups, I could spend a very long time talking about what they are, but basically today, all the zk rollups are just apps on Ethereum. They post data to the blob layer, and then they have a state transition function, and they verify zk proofs to facilitate deposits and withdrawals out of their bridge. However, it would be much nicer if the state transition function that these rollups are verifying is more native to the L1 and actually has L1 security and is upgraded through the same L1 governance process for a bunch of reasons. And so the vision for native rollups is that they're going to add a execute precompile to the Ethereum itself as a precompile that is powered by zk proofs of EVM block execution, and then rollups can use that precompile to get an inherent L1 security and become more secure and have better properties. And so there's a lot more that goes on here, but the idea is that native rollups will help rollups become more secure and better overall. And the way that native rollups can actually scale is through this real-time proving and zk verification. And I did a podcast episode with Justin Drake, who kind of came up with the idea and is publicizing it. And you guys should listen to that if you want to learn more, because it's a pretty complex technical topic, but it's something where we can scale the L1 and scale execution and make rollups much more native and part of the L1 itself, which also solves kind of other problems like interoperability and also conversations around Ethereum value accrual and future of the L1 scaling. And this has actually been a really serious effort as part of Ethereum. So they launched this ethproofs.org dashboard to keep track of progress towards real-time proving because they think it's really important to scaling the L1 and having this execute precompile. So if you go to ethproofs.org, you can see a bunch of zkVMs that are proving every 100th Ethereum block today. And we track metrics like cost per proof and the proving time. And so SP1 is actually on this dashboard. Succinct and Snarkify are two different provers that are generating proofs, but they're both using SP1. And you can see that SP1 is the #1 zkVM on ETH proofs, which is pretty exciting. And one of our biggest goals for our company is to actually hit that real-time proving benchmark of 12 seconds, at which point we can think more seriously about the execute precompile and actually implementing this native rollups roadmap. There's also been talks about enshrining RISC-V in the execution layer as well, which I think is really interesting. So today, if you want to program on Ethereum, you have to write in Solidity, which is not a normal programming language, kind of has a lot of drawbacks. And people are thinking that now that RISC-V zkVMs are becoming more common, and it's kind of the end game of zk verifiability, it might make sense to enshrine RISC-V as a more core concept to the execution layer. And so there's been people like Georgios and Ansgar, who's at the EF, talk about this concept. And there's even been a POC of R55, which takes RISC-V smart contracts and sticks it in Revim, which is the Rust EVM interpreter, as a proof of concept. So this is also a really interesting way to get more performant verifiability because the EVM has a lot of overhead, and also something I'm kind of looking forward to for zk more broadly in the Ethereum roadmap. And the last thing I want to touch on is thinking about zk beyond Ethereum. So we talked about zk rollups, we talked about native rollups and this execute precompile and real-time proving. And that all shows that Ethereum is really well positioned to take advantage of advances in zk and really use it as a core part of scaling their entire ecosystem. But actually, zk can help scale any ecosystem, and I think it's not just isolated to Ethereum. So, to take a step back at the last slide of our presentation, if you think about it, decentralization inherently has some overhead because everyone around the world has to re-execute all transactions and engage in redundant computation. And zk's succinctness property fixes this because you can have one person generate a proof, and then you can have everyone in the world verify the proof for much more cheaply than if they had to redo those computations. So with zk, you can have unlimited scale to blockchains without sacrificing verifiability. And Ethereum, I think, was ahead of the curve in recognizing this and really pushing zk and cryptography as part of its core roadmap. And Vitalik has obviously been talking about zk for a very long time. But now we can even see other ecosystems start to take advantage of zk and all these advances. So in particular, the Bitcoin L2 ecosystem has been a nascent area, and actually a lot of people in Bitcoin do use SP1 for their zk rollups or L2s or whatever you want to call them. We have a bunch of Celestia ecosystem rollups using zk in a much more native way. And even on Solana, you have concepts like network extensions, which are basically their rollup roadmap using zk as well. And there are a few builders in the Solana ecosystem who are building these network extensions with SP1 as well. So I think the final point that I want to drive home is zk is not just useful for Ethereum, it's actually useful for every ecosystem. And I think that's really interesting and a trend we're only going to see accelerate over the course of this year. Thank you.